Hello everyone, my name is Suyash Gupta and today I will be presenting our work Permission Blockchain Through the Looking Glass, Architecture and Implementation Lessons Learned. This work I did with Sajjad and Mo, and we did it at University of California Davis and for our startup Mocha Blocks LLC. This work will be presenting for Fab 20 and it will be part of the proceedings of ICDCS 2020. So what is this work all about? This work is about blockchain. What is blockchain? A linked list of blocks. Each block includes the hash of the previous block, and each block contains information about client transactions. What are the key components of a blockchain system? Blockchain system includes replicas that store all the data. It has clients that send transactions to processes. It has a consensus protocol that helps to ensure the client transaction is ordered across all the replicas. It has cryptographic constructs that authenticate replicas and clients, and a ledger that records transaction. This ledger is also the blockchain. If I ask you today, name some of the famous blockchain applications, you'll tell me Bitcoin, Ethereum, Algorand, and so on. Interestingly, most of these known blockchain applications are cryptocurrencies. Why is that the case? Well, the throughput of initial cryptocurrencies or blockchain applications was very low, around 10 transactions per second. While the throughput of existing distributed databases is very high, which is 1 million transactions per second. This low throughput is acceptable in permissionless setting. The aim of these permissionless applications is basically to make a cryptocurrency that is decentralized. The identities of the participant replicate are hidden and unknown. As a result, these applications suffer from forks in the chain. And due to their low throughput, they're not acceptable to industries. This led to the rise of permission blockchain applications, where only a select group of replicas can participate, although some may be untrusted. Identities of these replicas are known a priori. These permission blockchain applications prevent forks in the chain and are suitable for the needs of the industry. Further, they led to the rise of blockchain databases. However, the throughput of these applications is still very low, around 10,000 transactions per second. Often, when the reasons are asked why the throughput is so low, the key reason is that traditional BFT consensus protocols are expensive. So what is a BFT consensus protocol? Any blockchain application at its core has a Byzantine fault-tolerant consensus protocol. This protocol ensures the following. Given a client transaction and a set of replicas, the aim of this protocol is to ensure this transaction is ordered across all the replicas in the same manner. Now, existing permission blockchain systems blame this BFT protocol for low throughput. Hence, there is a rat race for creating newer and faster protocols. So we thought of asking a very simple question. Can a well-crafted system based on a classical BFT protocol outperform a modern protocol or permission blockchain system? In this case, let's have a look at this very simple graph. Here we have two lines, one for ResilientDB, another for another permission blockchain system. Here we make ResilientDB employ a slow BFT protocol, that is PBFT, which requires 3 phases, of which 2 require quadratic communication. And still, ResilientDB scales better than other systems, which require a very fast single-phase BFT protocol, Ziziva. So why is this the case? We believe existing permission blockchain systems are too protocol-centric, and they overlook the system design itself. Hence, ResilientDB adopts well-researched database and system practices. The code for ResilientDB is open sourced to use. So our first step was to dissect existing permission blockchain systems. On dissecting these systems, we found following. Most of the systems employ a single-threaded monolithic design. They employ no parallelism. The BFT protocols that these systems use have multiple phases and they can be easily parallelized or pipelined, but these systems avoid doing that. These systems integrate ordering and execution while they can be easily separated across threads or replicas. PFT protocol they use suggests strict ordering, but it's easily possible to relax this. Moreover, all the data has to be stored in memory. So there's a trade-off of using whether on-chip or off-chain memory. A lot of these permission blockchain applications employ expensive cryptographic practices like digital signature, threshold signatures, while there are cheaper, effective strategies like MAC. So here's the architecture for ResilientDB. It is a layered system. It has a secure layer for providing signing and hashing. There's a storage layer for storing all the data. There's an execution layer which executes and processes all the incoming messages. And there's a network layer for communication with the outside replicas and clients. ResilientDB provides a multi-threaded deep pipeline at each replica. Basically, in this diagram, you can see we have a lot of threads in ResilientDB. There are threads for creating batches. There are the worker thread for processing other messages. We have input and output thread for communication with the network. We have checkpoint thread for checkpointing and garbage collection. And there's an execute thread for executing all the transactions. So a key aim of this work was to evaluate existing permission blockchain system and try to see what are the reasons why their performance gets affected. Hence, we raised 11 distinct questions and showed different factors that affect the performance of these systems. In this presentation, we'll be discussing only 3 or 4 of them, and rest of them can be looked in the paper. For workload, we use YCSB, and for consensus, we'll use the simplest protocol, PBFT. Our first step was to see, is there an effect of pipelining and parallelization? Well, as you can see here, we start with a very simple case where we just have one worker thread, no execution, no batching, and nothing. And the throughput is very low. And as soon as we increased, that was, we got one execution thread, the work got divided. And obviously there's a higher throughput. Next, we thought of using zzva and seeing how does zzva performs in this setting, and we provided the same scenarios. And clearly zzva also gains throughput with more threads, but there are scenarios where zzva is having less throughput than PBFT. Then finally, we increased a few more threads. Now we brought batching threads into the picture. And clearly there are versions of PBFT which are better than a lot of versions of zzva. Finally, as you can see, we ended up providing a large number of batching threads and execution threads. As you can see, the performance is very high in this system. And clearly, there are cases where PBFT is outperforming a lot of versions of zzva. Basically, having a threaded pipeline system can help in getting more performance. Next, we thought of doing batching. Does batching always help the system gain performance? Well, as you can see, doing batching definitely helps in increasing performance, but only to a limit. After that point of time, the performance starts decreasing due to large messages. So an optimal batching size has to be found for each system. Next, we thought of checking out how does memory storage affects. Well, having in memory is definitely much better than having memory off the chain. Finally, we thought of checking, does having number of clients affect the system in any manner? Well, if you increase the client, then obviously throughput increases to some level, and after that, it constants out. But there's a severe effect on latency, the average latency. As you can see, more the number of clients, the average latency will increase because system gets loaded up with too many requests to process. So in the paper, we have many more other criteria that show how a permission blockchain system can get affected. Basically, we want to show that a fast consensus protocol is not always enough. It does not always imply an efficient blockchain system. We want to show that a well-crafted system-centric permission blockchain system can outperform a protocol-centric blockchain system. Moreover, we want system designers to understand that they need to dissect their application and find the performance bottlenecks. Thank you very much.